Hi there, welcome to my channel Mandu to Fundu. In this video, I am going to discuss about the solution for constructing a binary tree from the Postorder and Inorder Traversal output. Let's look at the problem description. We are given two integer arrays, which one is Inorder and the Postorder, where the Inorder is the output of Inorder Traversal of the tree, and the Postorder array is the Postorder Traversal output of the binary tree. So we have to return the root of the binary tree. Let's look at this example. So we are given the Inorder Traversal output and the Postorder Traversal output. So the output binary tree is represented as an array 3, 9, 20, null, null, 15, 7. So in the Postorder Traversal, the root node is present at the end of the out array, and for each subarray, the last element in that subarray is the root of that subtree. The Inorder array has only one element -1, and Postorder array is -1. Then the output tree is just a single node -1. So the constraints are the length of the Inorder traversal output is ranging from 1 to 3000, and the Postorder and Inorder lengths are equal, and the values are ranging from -3000 to 3000. And also in this tree, each value is unique. There are no duplicates, and each value of the Postorder also appears in the Inorder. So we are given two arrays. One is the Inorder output and the other one is the Postorder output. And let's see how we can build this tree. So in the case of Inorder traversal, nodes are traversed from left, root, and right order. In the Postorder traversal, first the left child and right childs are visited, then finally the root. In a given Postorder output, the last element in that output is always the root of that tree. So in this case, if we see, a 3 is present at the end, so this is the root node of the entire tree. And also the Inorder traversal traverse tree from left to right. For example, 9, 3, 15, 20, 7. Okay, so the position of this element is 0, position of this element is 1, this is 2, this is 3, and this is 4. Based on a given element index, we can compute the number of elements in the left and the right subtree using the Inorder output. In order to get the index value of a particular node in the Inorder output, we need to build the hash map. So first thing what we do is build a hash map which will contain the value in the tree and the index of that value in the Inorder traversal output. Okay, so each pair will have a value and index in the Inorder traversal. Then we call the helper function with in the hash map, and then the Inorder and the Postorder and the limit starting and ending index of that array. Initially we pass the entire array to that helper function. Then inside the helper function we pick up the root node of that Postorder output. So in a given Postorder output, the last element is the root of that entire tree, which will be built using that array. Okay, so in this case, if you see, 3 is at the end, so 3 is the root. So what we do, first we build a root node with that last element of the Postorder output. Once we did that, then we look up that root node value in the hash map we built and find the index value of that particular value in the tree. Based on that, we can compute the number of elements left subtree, and then depending on that we can adjust the array indexes, and then we build the left and right subtree recursively by adjusting the starting and ending index of the Inorder output and Postorder output. So once we come back from the recursive call, finally we can return the root node. Let's look at the flowchart. So input for this helper function is post order output array, in order output array, and the post order starting and post order ending index, in order start and in order end index, and then the input hash map. So this is the hash map built using the in order output. First we initialize the root, then we check whether the post order start index is greater than the post order end. In that case we return nil. Otherwise we create the root node, last element in the post order array, and then find that root node's position in the in order array and assign that to root idx variable. Then we can compute the left subtree size by subtracting the in order start index from the root idx variable. That will give a number of elements in the left subtree. Then using that information we can make a recursive call to build the left subtree and the right subtree out of the subarray. So for that subarray we for the case of build in the case of building left subtree, what we do is the post order array's new starting pointer will be the same POS, but the POS post order ending index will be the current POS plus the left count minus 1. Then the in order start index will remain same, but the in order end index will be the root idx minus 1. And then we pass the hash map as it is. So when we call this function, this will return the root node of the left subtree. Then we assign that to the root. We can make that node as the left child of the root. Similarly, in order to build the right subtree, we have to pass the post order start index will be current post order start plus the left count, and the post order end will be, we have to skip the root node, so that's why we do the current POE minus 1. Then for the in order output we have to pass the root idx plus 1 as the in order start, and in order end will be as it is, and then the hash map. So when this recursive call returns, it will return the root node of the right subtree. So that root will be assigned to the root dot right to make it as a right child. So we keep calling this recursively until all the nodes are processed. Finally we return the root node. Let's move on to coding. So first I build the map of int to int, which actually contains the pair of a value in the in order array and its index value. So this map will be used to calculate the number of elements in the left child. So for each value I assigned its index. Next I call the helper function with that in order map, and then the in order array and its starting and ending index, and the post order array and then starting and ending index of that array. Next I am writing the helper function. So in the helper function, first I check whether the post order start index is greater than post order end index. That means we have completely processed that post order array. So in that case we return the nil. So the root node value is present at the end of the post order array. So we assign that val variable, and then we find the index of that root node in the inorder output array. So we use that inorder map to find that index value. Then from based on that value we can compute the number of left child by subtracting the IOS from that root IDX value. Then we construct the root node, and then we make a recursive call to build the left subtree. Here we have to adjust the starting and ending index of the inorder array and the post order array. So in the case of inorder array, the inorder start will be same for the left subtree, and the end will be 1 less than the root index. And for the post order array, post order start will be same, but the post order end will be post order start index plus left count minus 1. Then we make another recursive call to build the right subtree. In that case we pass the inorder array, and then the starting index will be root IDX plus 1, and the IOI inorder end index will be same. And for the post order array, the starting index will be the post order plus the left count, POS plus left count, POS plus left count, and the ending index will be POE minus 1, because we already taken out the root, so we reduce 1 from the POE, and then finally we return the root node. Next I'm going to run the test cases. All the tests passed. Next I'm going to submit this program. Cool, this program is accepted. Next I'm going to do the code walkthrough with sample input. Okay, we have the input arrays post order and in order, and we have to build this tree. In the build tree function, first we create the in order map. So this will iterate over the in order array, and then for each value present in that in order array we create an entry with the index of that value as a value. So if you see here, the value 9 is at index 0, value 3 is at index 1, and value 15 is at index 2, 20 is at index 3, 7 is at index 4. So we build this in order map, and then we make a call to the helper function, which takes the in order map that we built, and then the in order array and the starting and ending index of that in order array, post order array, and then starting and ending index of that post order array. So inside that builder tree helper function, first we check whether the post order start is greater than post order end. That means we process that entire array. So we return nil in that case. Next, so in the post order output, the root node is always at the end of the post order array. So whenever we receive the post order array, the last element in that array is the root node. So here if you see, 3 is the last element, so that is the root node, and then 20 is the second last, so that is that's the right subtree's root node. So for each recursive call, we pick up the last element in the post order array and build the root node. Okay, so we pick up the last element pointed by the POE index, and then we look up that values index in the inorder array. Okay, so for that we look up the inorder map and get that value and assign that to root idx. Then if we subtract the IO inorder start index from that root idx, we can get the number of elements in the left subtree. For example, in this case, the first call, we have 3 is the root node, that is the last element in the post order output array. And then when we look up, the root idx is 1. Okay, so 1 minus the POS gives the number of elements in the left subtree, so we have 1. The left subtree contains only one node. Okay, so in the first call to the helper function, we built the node 3, which in turn make a couple of recursive calls. When these calls are returned back to this function, we built the tree like this. Next, create the root node with that value, and then we make a recursive call to build the left subtree, and then we make another recursive call to build the right subtree. Okay, so in order to build the left subtree, we have to pass the part of this inorder array and part of the post order array which contains only the left subtrees nodes. For that, we have to adjust the starting and ending index of the inorder array and the post order array. So in the case of inorder array, the left subtree contains starting from the current inorder start until the root idx minus 1. So the root idx minus 1. So this is the left subtree. So for this call, we pass 0, okay, so this call will build this left child. Okay, so when when this function is called, the POS index and POE index will be 0. So, and then this will build the root node, the node 9. Okay, and then when it returns back, the pointer to this node 9 will be assigned as a left child of the root node 3. Okay, then we are making another recursive call to build the right subtree. So for this, we have to pass this part of an array as an inorder array, and for the case of post order output, this part will be passed as the post order array in this recursive call. So if we look at it, the root idx currently it is 1. So 1 plus 1, 2 as the starting index of the inorder array. So if you see, this is the index 2 to 5. Sorry, 2 to 4. is passed for the in-order array, and in this case the post order will be the post order start plus left count, which will be 0 plus 1. 1 is the number of left child. So starting from index 1 up until the POE minus 1, because this is the root node, we already built the root node, so the remaining, this is the point 3. Okay, so earlier POE was 4, now POE minus 1, 3. So starting from index 1 to 3 will be passed to build the right child. Okay, so if you see here, when this call is made, we have the POS starting at 1, index 1, ends at 3. Same thing for the in-order array, it starts at iOS 2 and ends at IOE 4. So this call, which in turn builds the root node, and which in turn make a recursive call to process the left and the right child. So for that, again we do the same process, like build the root node and then find the index and then subtract the iOS from that root IDX, compute the left count. In this case, so frame to left child, in that case 15 is the left child. When this call, when it returns, it builds the node 15, and then the next recursive call build the node 7, and when this returns, when these two calls returns, they are attached to 20. When this function returns, this 20 will be assigned as the right child of node 3. Finally we build this tree. Next I'm going to do the time and space complexity analysis for this solution. Okay, let's do the time complexity analysis for this input. So this has 5 elements in it. So in order to build this entire tree, we have to traverse all the 5 elements. So in that case, the time complexity is order of n. So for this input case, this makes 5 recursive calls. And the space complexity is order of n, because we are creating the hash map of input data size. So in addition to that, we also use the stack space, which is at most the height of the maximum stack space used is the height of the tree, so which is order of log n. And if the tree is a skewed tree, then it will be order of n. So the worst case space complexity is order of n plus order of n. We are removing the constant term out of this, and the space complexity is order of n. Thanks for watching this video. Have a great day.